So far, our approach to statistical inference has been greedy for new data. So getting more and more data and increasing our sample size. These are the keys to making our inferences even more reliable. Now, the approach that we've been following is called a frequentist approach. But what about also using prior information or prior data? Well, if we wanted to incorporate that into a model, that's the idea behind Bayesian inferential statistics. Now, in this case, the graphical and numerical summaries that we've done earlier are going to stay largely the same. But here's where the difference occurs. Let's start first with just a simple example from probability to demonstrate the basics of how Bayesian statistics works. All right, suppose we've got two balls in a bag, and we know in advance that at least one of them is red, but we're not sure whether they're both red or whether one is red and one is white. Now, suppose I reach into the bag and it's a red ball that I'll pull out. Now, are you more or less likely to think that the other ball is red? Well, Bayesian statistics gives us a way to update our prior beliefs based on the data that we observe. Here's a table I want you to look at. Now, draw your attention to that first column. Here we see the two possible outcomes. Either both of the balls are going to be red, or one is red and the other is white. Right? Remember, we've drawn a ball. We know we've got at least one red ball. Now, that second column reflects our prior belief that both of those probabilities are equally likely. Notice that the prior probabilities over all the outcomes should always add up to 1. Now, we still haven't considered the observed data yet, right? The red ball in our hand. So our prior probabilities don't take that into account. We expect to merge our prior belief, that's called our current prior, with the data to now inform our decision. All right, check out that third column. This is what we call the likelihood. It's used for calculating the posterior probability, the probability that you would have observed the data if that hypothesis were true. Now, go through each of these hypotheses and imagine that is true. And then ask yourself, what's the probability of getting the data that I actually observe? So we can formally define the likelihood as the following. It's the probability of the data that you actually observe. In other words, if the hypothesis is true, what's the probability of getting the red ball when we do our experiment? So notice, in the first case, the probability of drawing a red ball given two red balls is 1. And in the second case, the probability of drawing a red ball given one red and one white ball is 1/2 or 0.5. Now the third column, this is the product of the prior probabilities and the likelihood. We call this the unnormalized posterior. It's only unnormalized because it doesn't add up to 1, right? But it's going to be proportional to the actual posterior probability, which we'll see in the last column. Now, to find those posterior probabilities, we take the prior, multiply it by the likelihood column, and divide by the sum. This is going to get us numbers that add up to 1. So in our example, we've got 0.5 divided by 0.75 for a posterior probability of 0.667. And then we have 0.25 divided by 0.75 gives us a posterior probability of 0.332. Okay, So that's now our updated belief about whether or not we've got two red balls or a red and a white ball. So having drawn one red, I'm now about 67% confident that the other ball is a red, and I'm about 33% confident that the other ball that we haven't observed is actually white. Notice that we've taken our probability, a 50-50 chance, and updated it based on our likelihood to get a posterior distribution. Now, Bayesian statistics is an entirely different approach for doing statistical inference. I mean, it's not just another technique like regression or hypothesis testing or ANOVA. The methods are based on the idea that before we ever observe any data, we've got some prior belief about it. Perhaps it's based on experience, or maybe someone else did a similar experiment 5 years ago, and so we have an idea of what our range should be. So as we observe new data, we use that data to update our belief. That's how the method works. All right, so we have learned a ton in this course, and a lot of it stays the same when we start to turn to the Bayesian world. Remember, we began with graphical and numerical summaries of data, where we first looked at histograms and box plots, numerical summaries. Those are going to largely stay the same. We also covered discrete and continuous distributions, along with special cases like the binomial or the exponential, the uniform, the normal. And again, in Bayesian statistics, those distributions stay the same. But we're often going to make more use of them in a variety of ways. In fact, things like correlation and covariance, those pretty much stay the same. But now here's where Bayesian statistics starts to go off in a world of its own. The way that we've been drawing conclusions about a population through t-test and hypothesis testing looks very different in the Bayesian approach to inference. All right, now in a frequentist approach, sort of in our frequentist world, we work really hard to get a random sample, right? We model the linear relationship between responses and explanatory variables. We attached a measure of confidence to them. Most of the methods that we learned so far, they take on this frequentist approach. Gimme, gimme, gimme. I need all the data I can. We assume our population parameters are constant. They're fixed, but they're unknown. So like the coefficients in linear regression, for example, are fixed unknown parameters. We also think of probabilities as sort of the long-run relative frequency in our frequentist world. So when we say the probability of heads is 0.5, we've assumed that we've flipped that coin an infinite number of times to get that probability, right? Probability in the long run. Also, our statistical analysis are judged by how well they perform in the long run in an infinite number of hypothetical repetitions of our experiment. So when we say we're 95% confident or a 95% confidence interval, well, that implies that if we were to calculate the sample mean 100 times, we'd expect 95 intervals to cover the true mean and 5 of them not to cover the true mean. That's that type 1 error. But frequentism, I'm not sure that's barely even a word, it isn't the only approach. In fact, over here in our Bayesian world, this approach is quite clever. Now, when we've got advanced information available, then Bayesian methods give us a clear way to update our uncertainty as new information keeps coming in. So for example, my prior belief that a coin is fair might be the probability of heads is 0.5. Now, I might observe 50 flips of a coin, and 42 out of those 50 flips were heads. So this might lead me to change my belief about whether or not that coin is fair. Bayesian methods can even be used to combine results from different experiments. So at its foundation, We use conditional probability theory to quantify the relationship between our prior beliefs and our observations. All right, so when should we go Bayesian? Well, it's pretty useful if we want to estimate a proportion, where you have a rough idea, but you don't really have much data. So maybe you want to estimate the proportion of people who smoke, or the proportion who like chocolate. It should be close to 1, I believe. But your uncertainty is described by a probability distribution, which is called your prior distribution. All right, so suppose you've got some data relevant to the thing that you're interested in. The data changes your uncertainty, which is then described by a new probability distribution called the posterior distribution. This reflects the information both in your prior and now with the data. So we saw that in our opening example. So in other words, in Bayesian statistics, we start with a parameter, and then we get some data, and then we update our parameter. And when we get new information, we should update our probabilities to take that new information into account. And so Bayesian statistics tells us exactly how to go about doing that. The posterior probabilities of the hypothesis, these are proportional to the prior times the likelihood. Saw that in our opening example with red and white balls. So if I've got a high prior probability, well, this is going to help my hypothesis have a high posterior probability. And a high likelihood value also helps. But to understand what this means, let's consider the meanings of the prior and the likelihood. Now, there are two things that can contribute to a hypothesis being plausible or reasonable. First, if my prior probability is high, that is, the hypothesis was already plausible before I even got the data. Second, if the hypothesis predicted the data well. So that is, the data was what I would have expected to occur if the hypothesis had been true. So now in Bayesian statistics, the terms in Bayes' rule, they have special names. The unknown parameter, which we call theta, is considered a random variable. So no longer is it fixed, like in our frequentist world, it's now a random variable, and we're going to assign it a probability. So we use a probability distribution, like normal or uniform, to describe the uncertainty in that unknown parameter. We call P of theta the prior probability, and that describes how sure we are that theta is true before we even observe the data. Once we've observed our data, we then want to update that parameter distribution using the famous Bayes rule. And then the probability of theta, given our data, is the posterior probability. It describes how certain or confident we are that our hypothesis is true, given the data that we've observed. So calculating these posterior probabilities, this is the main goal of Bayesian statistics. We also have the likelihood. So now this is the probability of data given your parameter theta. So if you were to assume that theta is true, this is the probability that you would have observed that particular sample data set. And then lastly, the probability of data is what we call the marginal likelihood. This is the probability that you would have observed the data, whether theta is true or not. So here we see Bayes' rule. We want to update the probability of our parameter theta given the data that we observe. We can reflect that by the probability of the data given theta times the probability of theta divided by the probability of the data. Now that denominator, P of the data, is a constant. It's fixed for our data set. And so we can really think of that posterior probability as being proportional to the product of the prior times the likelihood. And so the posterior of theta is proportional to that. Now, how do we back up an estimator for our theta? Remember, we're in the Bayesian world. Theta's not fixed. We've assigned a probability for it. But at the end of our experiment, I need something to give my value of theta to. How do I get that? What's my Bayes estimate of theta? Well, it's either going to be the mean or the median of your posterior distribution. You get to choose. In fact, in Bayesian statistics, both the mean and the median are valid estimators. Now, we're going to choose an optimal Bayes estimator by choosing the estimate that minimizes what we define as a loss function. This loss function is basically what we lose by using theta hat, so that hat means it's an estimate of the true parameter value of theta. A couple prominent ones, the absolute loss function. So this is just sort of the absolute value of our parameter theta minus what we estimate it as. A second one is the squared loss function. So now I'm taking that difference of theta minus theta hat and squaring it. Now for the squared error loss, the posterior mean is the Bayes estimator. And for the absolute error loss function, the posterior median is the Bayes estimator. Check out this graphic where we've got the absolute error in red and the squared error in blue. So depending on where your data fall along the x-axis, the squared error is the lowest or the absolute error is the lowest. So this is why you get to pick. There's not like a uniform estimate that's always going to be best. Now, one of the most common distributions that we use to place on our prior knowledge is a beta distribution. Now, it can be understood as representing a distribution of probabilities. In other words, it could represent all the possible values of a probability when we don't know what that probability is. All right, it's a bit confusing, so in fact, we're going to jump into this with an example. And here's my favorite intuitive explanation of the beta distribution. Now, if you pay much attention to baseball, you likely know that batting averages are, you know what they represent, right? It's the number of times that a player gets a base hit divided by the number of times he goes up at bat. So the batting average lies anywhere between 0 and 1. But a decent batting average, as you might know, is going to often range between, say, 0.25 and 0.27, while a batting average of over 0.3 is pretty excellent. Now, if I'm putting together, say, my fantasy baseball league, I might want to predict the season's batting average for a player at the beginning of the season, right? So what would you say if I predicted an average of 0.7 for this player? Well, you'd probably say I was crazy, right? The batting average is too unlikely to even be reasonable. In fact, we have some prior information about batting averages, right? Most season averages range between, say, 0.22 and 0.365. So notice there's a binomial distribution that's lurking in the background because at its core, the batting average represents a series of successes or hits and failures, which might be misses. So in situations where we want to place a prior distribution on binomial data, the best distribution to use is the beta distribution. In fact, we can use the beta distribution to represent our belief about the player's batting average. Here's how it works. The domain of the beta distribution is conveniently from 0 to 1. So that lines up with the appropriate range for our batting average. Now, we expect that the player's season-long batting average will most likely be around 0.26. That's about the average. But reasonably, it could range anywhere from, say, 0.2 up to 0.36. And this can be represented with a beta distribution. Here's the curve of that beta distribution in R. So assuming a season with, say, 300 at bat, A equals 78 could represent the number of hits, and B equal to 222 represents the number of misses. Now, conveniently, the mean of this data distribution is A over A plus B. So I specifically chose these values to give me a mean of 0.26. And the distribution, it pretty accurately contains our prior belief. Notice that the distribution kind of contains the values between 0.2 and 0.36. So this is sort of where we'd expect a batting average to fall. So that x-axis, it represents the batting average. It's a probability between 0 and 1. And the y-axis, this represents a probability density. So in fact, the beta distribution at its core is a probability distribution of probabilities. But here's why the beta distribution is so amazing. Right? Imagine that our player gets a single hit, right? His record for the season is now 1 hit for 1 time at bat. So we can update our probability given this new information. All right, this new beta distribution is going to look like a beta with A naught plus the number of hits and B naught plus the number of misses, where now A naught and B naught are the parameters that we started with, 78 and 222. So in this case, A increases by 1, right? His 1 hit. And B, it doesn't increase at all, right? There's no misses yet. So this means our new updated distribution is beta of 78 plus 1, or 79, and 222. Here's a graph of that distribution, and to the naked eye, it looks pretty close to the one we saw before. You can't really tell the difference. But suppose halfway through the season, he's been up to bat 300 times, hitting 105 out of those times. So now our new distribution would be a beta of 79 plus 105, right? We're getting that because we're adding the total number of hits for A, and then B would be the total number of misses. So 222 plus 195. So this curve is now a little bit thinner and is slightly shifted to the right to reflect that higher batting average. In fact, we could calculate the new expected value of our posterior estimate. So this would give us an estimate of the player's batting average. We calculate that as A over A plus B. So after 105 hits and 300 real at-bats, the expected value of this new beta distribution is 79 plus 105 divided by 79 plus 105 plus 222 plus 195 to give us a batting average of 0.306. So notice here, our updated Bayesian batting average is lower than what we would get in our frequentist world, right? The frequentist estimate would just be 105 over 300, 105 plus 195, to give us a batting average of 0.35. But notice also that Bayesian estimate is higher than the prior belief we started with, or 0.26. So the beta distribution is best for representing a probabilistic distribution of probabilities, the case where we don't know what a probability is in advance, but we've got some reasonable guesses. Now, the Bayesian framework allows us to dynamically update our prior beliefs, considering various types of distributions for our prior probability. We could do a uniform prior. So in the absence of any other information, a uniform prior, or just a constant prior, is often assumed, meaning every possible value has the same probability of being selected. Now remember, a random variable has a uniform 0-1 distribution if its PDF, or its probability density function, is constant over the interval from 0 to 1, and then a 0 everywhere else. On the other hand, the beta distribution, beta evaluated at our parameters a and b, this is another commonly used distribution for a continuous variable that can only take on values in the interval from 0 to 1. Here's the probability density function, and it's going to shock you because it's got some new stuff in there that we haven't seen before. So our beta distribution looks like gamma of a plus b over gamma a and gamma b. This is just a constant because remember we set values for a and b, times x to the a minus 1 and 1 minus x to the b minus 1. So that gamma distribution for whole numbers or natural numbers is just the number minus 1 factorial. And our x value ranges between 0 and 1. We'll look at some plots of those in a second. But notice one thing. The gamma ratio in the front is just a constant. So we can solve for that only if we need to integrate the function to 1. The most important part of that variable or of that distribution is the x's. X to the a minus 1, 1 minus x to the b minus 1, because that tells us the shape of the curve. All right, check this out. Notice the uniform 0, 1 is a special case of the beta distribution where a equals 1 and b equals 1. Notice the shape of the distribution changes when a and b are much less than 1, as you see here, or much greater than 1, when you see here, or for every possible value in between. Now, what's important to remember is that the shape of the distribution is describing our prior belief about a probability. So if I wanted to place a prior distribution on the probability of, say, a mechanical part failure, I might use a beta prior of a equals 0.1 and b equals 0.9. Since the shape of that distribution, as you see here, has the highest probability close to 0, and it quickly tails off. Let's do an example. Suppose we have a coin that may or may not be biased, and we want to estimate the probability of heads. Well, our prior belief might be that the probability of heads is 0.5. So we conduct 15 independent trials, and we observe 10 heads. So this is going to result in a binomial distribution with n equal to 15 and a probability of p. Let's find the Bayesian estimate for p, the mean of the posterior distribution, using a beta prior distribution. All right, so then how do you choose a beta? Well, one way to do it, like we did in our baseball example, is to choose a beta prior that has values of a and b that match the mean of your prior belief. In this case, our prior belief is 0.5, so we want to choose values that give us a mean of 0.5. Notice here, if we choose a equal to 4 and b equal to 4, we get our prior distribution. Here you see a and b plugged in. And notice that we can solve for the expected value of p as a over a plus b, or 4 over 8, to give us an expected value of 0.5. So that might be a nice starting probability for those parameters. All right, so now we have to calculate the posterior distribution. Remember, this is the distribution of our parameter p given the data that we observed, x equal to 10. And we know that's going to be proportional to the product of the prior times the likelihood. In this case, our prior for p was a beta with a equal to 4 and b equal to 4. And our likelihood was the binomial with x equal to 10. So notice when we write those equations out, ignoring their constants, we get the posterior distribution, p to the 13th times 1 minus p to the 8th. Now notice your posterior is actually a beta distribution with a equal to 14 and b equal to 9. So in fact, we know what the expected value of this posterior is. It's 14 over 23. or 0.6. Now, in the frequentist method, our estimate would have been our observations 10 out of the total number of flips, which is 15, or 0.667. But you see where the Bayesian estimate has taken into account our prior belief to now update it. Visually, here's what that looks like. Notice the red line in the background is a plot of our prior belief. And the posterior is the plot after we've updated our estimate based on that prior belief. So notice the mean of the blue distribution has shifted closer to 0.609. Now we could also show all three of those distributions together. Here's the prior times the likelihood to give us the posterior. Notice the prior is sort of placing higher probability in the center, less probability in the tail. And the likelihood, this is the data that we actually observe. And notice how based on that likelihood, our posterior has shifted, sort of taken information from the prior and updated it with the data or the likelihood. Now, in the case of the binomial likelihood, any beta prior that we use is still going to give us a beta posterior distribution. So when a prior and a posterior belong to the same family, we call this a conjugate prior. In this case, the beta distribution is a conjugate prior for the binomial likelihood. Now, conjugate priors are immensely useful because they provide a simple analytic solution to this type of inference problem. And in fact, we can easily know the mean and the variance, for example. But conjugate priors are also somewhat limiting, since our prior belief might not be representable using a conjugate family's parameterization. Now here, let's suppose a Bayesian and a frequentist walk into a bar, and they start talking about their drinks. The Bayesian says, hey, this isn't our first time in a bar, so we should start from what we know we like and incorporate that prior probability. I mean, rarely do we have no idea of the type of drink we might prefer. And so if a prior is truly unknown, we could just use a uniform prior, because then we get the same results as the frequentist method. But the frequentist, on the other hand, is going to say this. Well, choosing a prior, this allows us far too much subjectivity. In fact, you could pick a prior, I could pick a prior, the bartender could pick a prior. We could apply all of our priors to the same set of drinks and come out with very different conclusions. The best thing to do is to take random samples of all of our drinks an infinite number of times. All right, all jokes aside, herein lies one of the pitfalls of Bayesian statistics. 3 different people can choose 3 different priors and analyze them on the same data set and get 3 different posteriors. Now, a good informative prior will typically be based on a very similar study done under similar conditions in the past. But these aren't always available or applicable in every situation. And it's also not as easy to write out the posterior distribution that doesn't come from a conjugate family. All right, let's suppose your data followed a beta distribution and you wanted to use an exponential prior. Well, the posterior be like a beta times an exponential, and what does that look like? Right? We don't know the mean or the variance of that. And it's actually more computationally intense to try to estimate those. On the other hand, a Bayesian would complain that a frequentist assumptions about long-run testing over an infinite number of hypothetical repetitions of an experiment, it might sound good, but it's usually not realistic. Bayesian methods better approach how we already think and the type of problems that we often encounter. So in my view, there are benefits to trying both frequentist and Bayesian approaches, and doing so early on, because Bayesian methods will always default to the frequentist method with a non-informative prior, like the uniform distribution. So you've got nothing to lose and an entirely new world of Bayesian statistics to gain.